Well, welcome back, and let's talk a little bit about mean and variance of a binomial distribution. These calculations are mathematically fairly easy, but it can be a bit tricky to understand why, and at the moment it doesn't matter too much as we move forward. So consider this. I roll a dice 12 times. How many sixes do I expect to get? Now, if you just do that in your head, you might be thinking, well, if I roll a dice 12 times, I'm probably going to get one of everything every 6 rolls. So I should get, every 12 rolls, I should get 2 sixes. That makes sense. 2 sixes, 2 fives, 2 fours, 2 threes, 2 ones, and 2 twos. That gives me 12 different rolls. So I could get 2 sixes. This should be the most likely. But I could also get 1. I could get no sixes. I might just be unlucky. I might get a few more. And if you play any dice games, you might be hoping for more sixes. I might get 7 sixes out of 12. And that might be great. I could get 12 sixes. It's really unlikely, but I could get 12 sixes. But we know that 2 is probably what we expect to get. And there is a really good reason why. And that is this. So we know that we call our what we expect to get E of X. And what we expect to get is NP, which in this case is 12 rolls times by the probability of success. If we roll a dice 12 times, we expect to get a 1/6 of the time. That will give us an expected value of 2. And it turns out our expected value is also called mu, or maybe X bar, and it's our mean value. So you'll see it referred to as the mean. So the expected value is NP, and it's the mean, what we should get on average. We also have our variance, and you're welcome to have a look at why this works, but for now you just need to see the calculation being able to apply it. So the variance, which is the spread of the data, is calculated by doing n times p times q. And the p and the q, basically if p is quite high, 0.95, then it creates a larger expected spread, and so you'll end up with a larger variance because you're expecting more in a particular way, whereas it's centered more if p is centered more. So that's what this variance calculation does. But as long as you know that the variance is npq, or n times p times 1 minus p, because we know q is equal to 1 minus p. And we also know the standard deviation is the square root of the variance, which we've traveled through before as well. Then you'll be able to do these calculations. So let's have a look at example 5. Historically, I've won 2 out of 9 games of Spider Solitaire. If I play 13 games now, while you complete exercise 15b, what is my expected X and my variance of X? So we recall that the expected X is equal to NP, and in this case, N is 13 because I'm playing 13 games, and P is my probability of success, which is, so not 2 over Q, 2 over 9, which is based on data is 2/9. And so I get 13 times 2/9, which is 26 over 9, and 26 over 9 is something like about 2.77. So I'm expecting in 13 games to win about 2.77 games, which I won't win. I won't win 2.77 games because this is a discrete distribution, but it means that 2 or 3 are most likely. Be a little bit wary. Just because that's closer to 3, it does not mean that 3 is the most likely. Depending on how the data is spread, 2 might still be most likely. And so if you get a situation where you actually have to pin the most likely discrete outcome, if you got 2.77, you would now work out the probability of 2, work out the probability of 3, and compare them. But it doesn't really indicate that here. I just need to calculate my expected X, and so there it is. And my variance of X is equal to NPQ, or NP 1 minus P, which is 13 times 2 over 9 times 7 over 9, and that's equal to 13 times, well, I'll do this in the calculator, 13 times 2 over 9 times 7 over 9, and that's equal to 182 over 81, or 2.247. So 182 over 81 or 2.247. And that's all you've got to do for these types of questions. Now the variance of course measures spread. So you might have to then do a comparison between two distributions by talking about one having a higher number, therefore it's more spread out.